Java collections are, they've used generics to create the prototypes for some very common data structures, like stacks, linked lists, trees, and that kind of thing. So we get to use them, so we can declare variables. We can, for example, instead of coding up all the functions for a stack, we could just use the Java stack, and we could say, well, I'm going to make a stack of integers, rather than code up all the integers for us. So let me just go over a few properties of the Java Collections API. They're not used for array, like, so for example, an array, which is not part of the Java collection. Arrays can store primitive types. Primitive types like integers, floats, and you know, double and that kind of stuff. You can put those into an array. When we do the collections do not do this. So the collections, we'll go over this shortly, is a set of all the different structures like an array that we could use to store stuff. But we can't, will not store primitive types. Say primitive types. Okay. But then we have those wrapper classes. Java has those wrapper classes, like, for example, so just a little refresher, if we said integer x in Java, what does that mean? We declared a piece of storage called x, and x can store a value in it. We could say the integer equals 0, and that would be fine. We'd actually declare a piece of storage like that. In Java, if we say, let's say we made a class called playing card. And we made a playing card, PC. So this was a class that we created, let's say. If somebody says playing card PC, and that's it, what did we create? Did we create a playing card? Did we create a piece of storage? And let's say the playing card has two fields, like it's rank, suit and rank. Did we actually get a chunk of storage for the card? Or what are we doing in Java? So this is actually different between Java and a language like C or C++. When we declare something, do we get a piece of storage for it in Java? So in Java you don't. If you actually want to get a piece of storage, you'd have to say equals new and then playing card. And then maybe we could have a constructor that we can initialize it to, let's say, the king of hearts. And now we would get, so this new actually goes and gets us a piece of storage. So this ends up being just a reference to an object. If you actually want to get the object to be created, you have to say new and then whatever the name of the object is. Okay, so this is a reference, and this is what's, I guess we'll consider a non-primitive type, something that we made up ourselves. Primitive types are the types the compiler gives to us. So, collections can't be used to store primitive types, but if you wanted to have an integer, a primitive type, be like a referable object, you could use integer. Integer x, and then you could initialize it to say 5, and now x is a reference like a non-primitive type reference to an integer, and then we could use that for the collections. Okay. Okay, and the collections are stored in Java util dot collections. So in order to use them, you would have to include Java util. So you could do, like, so for example, you could say import, maybe I should do that in a different pen. You could say something like import, and then say Java util. You could then say star, which will get collection plus everything else. You know, when you put that at the top of your file, you can now use the collections. Okay? So, you put that at the top of your file, and now you're ready to start using the collections. Okay, so now, let's go over just some of the overall ideas of the collections. We could have types that are sets. Okay? So what we can do is, we could make a group of things be a set, and they cannot contain the same value more than once. So what would be an example where you'd want to create a set? Like, we've created arrays before, and that's like if you have a group of things that you want to have laid out in storage next to each other so you could reference them by an index. But where would be something we'd want to have a set for? So for example, let's say, back to the playing card example, suppose we have a deck of cards and we're dealing cards out to a player. There's really no such concept to the player as like card number 1 and card number 2. They're just a collection of cards. So we could create a set for the player and then just add them to the set. So so that could be like an example of a set where it's basically, so this is kind of at a high level, we're talking about sets. We're saying that a set is a collection of stuff that really doesn't have any order to it. So if you ever need a collection of things that has no order, you could create a set. Another thing would be a map. Okay, and a map uses a set of keys to look up values. So an example of a map, and like us, do you have any questions? Or?
If you get same cards.
Yeah, so a set, for example, if we did decide to have a player, a card player, you have a set for their cards, you cannot contain the same value twice. So if our deck had 2 King of Hearts, and you gave it to the player, they would only accept 1. Actually, I'll go over an example of that in a second. So now the question is, let me say that, because another interesting thing that'll come up is, if we make up something like a card, right, which has a suit and a rank and kings and queens, Java doesn't know what kings and queens are, only we know what they are. We have to be able to tell this thing what it means to be equal. We have to explain what being equal means. So that way, if they're equal, it won't accept it. So yeah, I'll get to that in a second. So a map ends up being a set of keys used to look up a value. So a map is something like, I'm sure you have this on your cell phone. So you have a group of people's phone numbers, but it's hard to remember people's phone numbers. You know people's names. So in your phone, you type in a name, and you map it to a phone number. Now, if you want to look up a phone number, you actually can just look up the name. You find the name, and it tells you the phone number. So a map is something that has, it's a set of key values for looking up other values. So for example, you could have name and number. And so you have a bunch of names and a bunch of numbers. And you're saying the name, somebody's name maps to a certain number, and now you could look up the number by a name. So it seems like an abstract type, but you use this on your cell phone. So, okay, then let me just go like into, so these are pretty high level descriptions of values. And then, so for example, let's go back and consider an array. An array which is not part of the collections, that came with Java before the collections came. So an array is used is for fast access. Okay, so now basically what we're starting to realize is we have pieces of storage like arrays, maps, sets, things that hold other stuff. So they call it collections, I guess it's collecting all these items together. But these are basically structures that hold other stuff. So, why would we have so many different items? Why shouldn't that just be one structure that holds everything? And the reason is, depending on the structure we use could determine whether we can insert into it very quickly, or maybe it takes a long time to insert into it, but when you do a lookup, when you go to find something, you can find it quickly. So for example, if you stored all your friends' phone numbers but didn't put names on them, how would you ever find a number? You'd have to look through all the numbers until you see the one that matches it. You'd be searching every one. But if you map names to numbers, you can just look up a person by the first letter of their name and you'll find them very quickly. So just as the example with the cell phone, to add data into your phone takes more work because you have to put in you have to create a new user, type in the name, type in the number, and then save. It takes a long time to enter it, but once it's all entered, lookups are very quick. So depending on what you're doing, do you want to have a structure that you can add stuff quickly? Then a map's not a good thing. An array would be a good thing because you can just add it to the end. But now the problem is if you want to go looking for something, you have to start at the beginning and walk all the way through looking for the thing you're looking for. So maps are good for looking things up, but they take a while to enter them. Okay, so an array is meant for fast access, but it's not good as it gets large. An array of 10,000 things, it'll be too difficult to look things up. A linked list, so I'm just going over some of the data structures we've talked about before. A linked list is a structure that has, say, a reference to the first node, and then the nodes are actually separate. They're not like an array where they're next to each other in contiguous storage. And then let's say here's the end of it, and the begin. So what's good about a linked list is that you can insert new elements into the middle. Like with an array, we cannot insert new elements into the middle because they're all in a row. And if you wanted to insert something in the middle, you'd have to take everything from that point down and copy it to the next box over. But here we can just create a new node. Let's say we wanted to add a node between this one and this one. We can just create a new node anywhere and then make this reference refer to this one, and then this one refers to this one. So these arrows, these are not like pointers in C or C++, these are references. So there's a field referring to the next object in the linked list. Okay. Then another style of a collection is a hash. Okay? So a hash is basically saying something along the lines of, I'll draw kind of a simple model of a hash. But a hash could be, let's say we had an array of, say, 10 numbers. 10 different buckets of data. And then after that, maybe we had a linked list of items coming out of so this is really a hash of linked list. So suppose we have an item that we want to store into a structure, and we would like to be able to look up the value pretty quickly. So we don't mind taking a little time to store it away, but if we go to look up something, we want to find it pretty quickly. So it's kind of like the cell phone. You're looking for a friend, you want to find it quickly. So this would not be a map where we're mapping one value to another. What we're doing is we're taking the value we're looking for and we're running it through a function, let's say a hash function. We'll call it HC, because in Java they call it the hash code function. And this thing will tell us as an answer, oh, it's in this bucket, or it's over in this bucket, or it's over in this bucket. It'll tell us where it should be. And then we would just jump to that structure, which in this example I'm saying is a linked list, and find it there. But hopefully these are fanned out enough that we could find it very quickly. So for example, let's say they were integers and we decided to make our hash function would be to just take the last digit of the number. So let's say, this is not a great hash function, but let's say it was 629. So we say this number goes into bucket 9. So then we would go to bucket 9 and then know it's somewhere over here. We don't have to search for these things. So our hash function would basically just say what is the last digit, and that would be, it would return 9 as the answer. And then we go into bucket 9. Okay, so hashes are not good for, these are, so what's the advantages and disadvantages of hashes? It's advantageous for fast lookup, fast lookups, but it's slow for storing. Well, no, actually it's not that bad for storing. So we run the hash function, then we know where the bucket it goes to, and hopefully, if we have a long enough range for this array of buckets to put it in, hopefully we don't get too many duplicates. What I mean, what I'm building a linked list here is if you happen to have what they call a hash collision, meaning two different items belong on the same list, then we have to somehow store them both. So it's fast for storing. But what's the downside? The downside is it only works if this array is much, much larger than the number of items we're storing. Because if it's very small, like let's say it went from 0 through 9 and we stored 10,000 numbers, each of these lists would be like 10,000 divided by 10, they'd be pretty long. So it's really like using a linked list. So it's really meant for the amount of storage we're going to use up is going to be pretty large compared to the number of items in the hash table. So it's not good for small number of elements. So a hash wouldn't be good if you're only storing 10 things. There's no point in making an array of 1,000,000 and a hash function that makes them fan out into 1,000,000 different buckets if there's only 10 things we're looking for. Just to use an exaggeration. Okay. So let's say. Okay, so now let me go back to talking about sets again. So we're talking about these containers at kind of a high level. We could do some concrete examples after. So for example, suppose we had code that went like this. We should use a different color. Suppose we had some Java code that went like this. So this is an example of what I mean where this is the non-primitive type of an integer. The word integer spelled out. So what I'm saying is now this is a reference to a non-primitive integer. So now I have to actually, it's not a piece of storage, it's just a reference to a piece of storage. So now I have to say it equals new, and then I create an integer of value 6. So that's just like a little refresher of, non-primitive versions of primitive types. Now suppose we want to have another integer. Another 6. Okay, so now we have two separate pieces of storage called a 6 and another 6. Okay. Now suppose we said my set. Now obviously we've created my set above here. Somewhere in here we created the set, but we're saying my set. So I've created a set called my set, and then I'm using the sets have an add function. I'm going to add a 6. So I couldn't have put an integer, I couldn't have put an int into a set, because sets don't accept primitive types. But this is the non-primitive version of an integer, so it'll accept that. Now suppose I said my set add another 6. Would it add this other 6 to the set? So we're saying that sets do not allow duplicates. Would this be, so these are two different pieces of storage. Both of them have the value of 6. And then what ends up happening is, what? Would they be considered equal? And if they're considered equal, it would be added to the set. So the set, I can just kind of draw the set as a cloud. This is my set. And it has A6 is in it. And now we're trying to add another 6 to it. It doesn't allow duplicates. So what would determine if this would add it or would it not add it? So it really depends on what is the definition of them being equal. What would make them equal? So what makes them equal? Now the set has a type called, the set is of type integer. So the only things allowed into them are integers, not ints, but integers. So what would determine if two integers are equal to each other? What
It may show the same value.
what, the value inside the variable is the same? So okay. So if the values equal to each other, like maybe, you know, like if you said A equals B, if A equals B, that means they're equal, right? So like in C and C++, you could, see, what I'm saying right here is, what is the definition of equals? Is it that the values are equal? Is it if this operator decides that they're equal, like, in other words, what is the thing that determines, yes, they are equal, no, they are not equal? So, if you've used C or C++, we would actually have to overload this operator to say, I'm going to explain what it means for this to be equal to this. So for example, if we had the playing cards, maybe we decide that if the ranks are equal, the cards are equal, and we don't care about the suit. Like we're kind of making it up. We could do that. We would have to write a function called equals that says a king equals a king and a queen equals a queen and so on to explain what it means to be equal. What Java did is they have a function called equals. Equals with an S or without an S? Equals with an S. They have a function that every class has called equals. And we can rewrite that function. So what it really comes down to is if the equals function says they're equal, then since they're equal, they won't be added to the set. So we actually, there's an equals function that determines whether or not these two things are equal, and whatever we put in the equals function will determine if they're equal or not. Right now, the equals function by default will just compare the two values, but we could change that to anything we want. So when we go to create sets, we want to make sure that we write an equals function in case the things we're throwing into the sets, like playing cards, if the compiler can't figure out what does it mean to be equal, we would want to explain in that function what it means to be equal. Okay. Then another routine that we might have to overwrite is, and this would show up in the hash codes. So let me erase all this now. So really what I'm just trying to get at here is some of these collections perform operations where the compiler needs to know what it means to be equal. And then it might even need to know what it means to be less than or greater than for some of the collections too. So let's say we did this. Let's say we had a class that looks like this. Okay. So now back to the hash example. Hash me. So what I'm doing here is basically we're writing the equals function to describe what it means to be equal. So I'm going to pass in an object into equals, an object called that. Well, let me just finish writing out the code. So that. So in this case, what I'm doing is I'm saying, making a class called HashMe, but so this is a class that has three fields, A, B, and C. We could think of this as like the suit and the rank of a playing card, but there are three fields that have meaning to us, because we made this thing up, and the compiler really doesn't know what it means if two objects with an A and a B and a C are equal to each other. So we're going to explain to it what it means to be equal. So we're going to write a Boolean function. So equals is either true or false. If I say, is this equal to this, it's either true or false. So it's a public method. So these fields are private, which means you can't access these from the outside. Public means you can access this function. So equals takes in an object called that. Now you might think the object should be of type HashMe. But somebody might compare a HashMe item to something that's not a HashMe, and if they're not the same type, we'll say they don't equal. So the first thing we say is, if that is not an instance of HashMe, if they're not the same type, then they're not equal. That's false. Now we'll create an object of type HashMe called H. And we'll take the thing that they gave us, which was of type object, and we'll cast it back to HashMe. Does that make sense? So you might think, why didn't we just do this? Why didn't we make this of type HashMe? And then we don't need this line, because it already came in as a HashMe. The reason is somebody might try to compare a HashMe to a non-HashMe. And if they call equals, this will break because the typing passed in didn't match this thing. So we made an object, and object, remember in Java, that's the base class of all classes. So everything is of type object in Java. It'll never fail. So you could pass in, you could create something called a playing card and pass it in as an object. It'll come in, and in order to get it to turn back into a playing card, you'd have to cast it to a playing card. It means switch the type back. So that's why we're doing this. We're saying, bring in an object, then we're saying, if the types don't match, return false. Now we're saying, whatever you gave us, let me convert it, because now I know that the types do match. Let me convert it back to a HashMe, so that becomes H. And now I'm defining that if field A of this object and the field A of the thing that was passed into us match, and field B's match, I should make these big, all big letters. Fields B match, then I'm considering them equal. So in this definition, I don't really care what C is. If A's matches and B's match, they're equal. It's like something I'm making up. Just like with the playing card, we could decide that a queen of hearts and a queen of diamonds are equal. Even though the suit is different, if we decide that the rank determines which one's better, we could define equals to say the suit matters and the rank matters and the suit doesn't matter. So really, so we wrote this to say A and B matter but C doesn't matter. We could define equals any way we want, but we would have to define it. And then once we define equals, then we could, then anything that needs to know if something equals or not, like a set, needs to know if they're equal before they let it into the set, we've now defined it. Okay. Now suppose we wanted to put items into a vector. Let's do a different, let's look at a different collection. We'll look at vectors. Well, wait, no, let me do one more function we might have to override. Let's do a hash set. Wait a second. No, let me do, what's an interesting one? A tree. A tree set. Okay. So a tree set. And what I'm kind of doing now is I'm just kind of randomly picking ones, not randomly picking ones, but I'm picking ones that will cause us to need a new function being written. But a tree set is a special type of a set that organizes a set of stuff, but in an orderly way. So for example, if it's like a binary search tree, it might be structured like this. We might have a structure, so for example, let's say you were throwing stuff into a set, but the set has lower values on this side and higher values on this side. So maybe, for example, suppose we had cards in a deck. Suppose we had a 2 of spades, and then a 4 of diamonds, and a 5 of hearts, and a 7 of clubs, and a 10 of hearts, and a queen of hearts, and an ace of spades. Let's say these are our cards in what we're calling a tree set. So Java allows us for a tree set that's not in the C++ standard template library. But now an order is maintained. This card is less than this card, so it's kind of a left to right order to it. So now if we decided we want to go looking for a card, there's an advantage to having it structured as a tree. If we wanted to say to ourselves, do we have any 10s? What we can do is we can go to the top node and say, we're looking for a 10, which is higher than 7. So we know if there is a 10, it's over this way. There's no 10s over here, right? So we know to search here. If the thing we're looking for, a 10, is less than a queen, we know to go this way. If it's greater than a queen, we know to go that way. So we can look here, then look here, and then look here. We only have to look at 3 spots to find the 10. We don't have to look at all of them. If this was an array or a vector, we'd have to look through all of them. So this structure is kind of sorted. Now here's the problem. We're going to be adding items to this tree set. How did it know, let's say this 10 was not here right now. Let's say the structure looked like this. And I'm now adding a 10 of hearts to this structure. How would it know, how does it know that a 10 of hearts is bigger than a 7 of clubs? We would have to tell it what it means for one thing to be bigger than another, right? So, and let's say a 10 is a 10 bigger than a queen. The Java compiler doesn't know that. We would have to teach that to it. So, in order to get this to work, in order for it to know a 10 is bigger than a 7 but less than a queen, so therefore it should insert it right there. In order to know that, it has to know, it's a 10 of hearts. It has to know which cards are bigger than other cards. So what we'd have to do is we'd have to implement the comparable interface. Which has a method called compare to. Compare with a capital T. Compare to. There's a method called compare to. And the method compare to is where we have our opportunity to write in the code that says an ace beats a king, and a king beats a queen, and a queen beats a jack, and a jack beats a 10. We would have to do all that. So now we have an item, we have an object, and then we're going to compare it to another object. So if I have an example. Well, the example would go something like this. We would say, the code that's inside the tree set, at some point when we get this new item that we're inserting, it's going to say, is this thing bigger than this thing? is 7C, 10H, which one's bigger? 10H, QH, which one's bigger? So how would it know which one's bigger? It's gonna call the compare to method. And the compare to method is initially blank, so we would have to fill it in with data. So the data would be something like, if ours, let's see, if rank equals ace, and this wouldn't be the smartest way to do this, and the thing that we got in and objects, we'd have to cast this back, so we'd have to cast this back to a card. Object dot rank equals king, then return so what compare to should return, what should it return? It has to return three things. It could either say A is greater than B is greater than A, or they're both equal. So what it ends up doing, it returns a negative number if this item, the item that is being called for, is bigger than the one being passed in. It returns a 0 if they're equal, and it returns a positive number if the item being passed in is bigger. So we would have to actually spell out if the rank of our card equals ace and the rank of the card that came in is king, then we're bigger, which means we would return -1. And then we'd have to cut and paste this for all the aces and then all the kings and all the queens. We'd have to spell them all out. There's probably a smarter way to do this, but we would have to overwrite the compare to method, and we would have to implement, I don't know if you remember implementing interfaces, we would have to implement the comparable interface, which has the one method compare to, and we'd have to overwrite the compare to method. And that it's in this code, we write this over and over. Oh wait, so this should be else. If this is an ace and this is a king, sorry, that would be -1. And we could write in every combination to describe if one card is this and one card is this, whether it's true or false. And then once we've done compare to, then we can use tree sets, because tree sets can now figure out which one's bigger than the other, and that's how they can maintain them. Okay, maybe what we could do in the next class is we could go over concrete examples of Java. I could put them on the projector, and we could watch how it works for real. I just wanted to get, this is just kind of like a high level of the way collections work, that we have structures. There's many different structures, and the reason why there's many different structures is there's no structure that's the best one. It really depends on what you want to use it for, will determine which one you pick. So for example, if we wanted to, if you were writing some code that took in a bunch of playing cards and you needed them in a particular order and you can grab them pretty quickly, and you don't insert into this thing too often, then a tree set could be a good data structure to use. If you are constantly inserting and don't really care about the order, then maybe an array or a vector would be good. You just keep adding them to the end, right? And you don't care if they're in order. This is better if you don't insert too often, but you start looking up stuff right away. The same idea with your cell phone. If you had a cell phone for some reason where you're constantly adding new people, but you never really call anybody, you might as well just add the number and forget the name, because you don't really call anybody. But if you very rarely add a new person, but you're constantly making phone calls, then you want it to be very organized, so you can find people quickly, because you're constantly looking them up, but very rarely adding them. So you don't mind when you add them, you have to add all that information, because now you're all set up to find them quickly. So it's basically, it's the same trade-off here.